When we look at genotypes and we look at phenotypes, what we see in blood typing is the following. If we look at blood type A, there are two ways to write it. We can write it in the homozygous condition, okay, which is two dominant genes or two dominant alleles together, or we can write it in a heterozygous condition, which is one dominant gene and one recessive gene together. If we look at blood type B, there are also two ways in which to write it. We can again have a homozygous condition, okay, where you have two of the dominant genes together, or you can have a heterozygous condition where you have one dominant and one recessive gene together. We've already mentioned that the only way to get blood group O is to have two recessive genes together, and we also know that with blood group AB, there's only one way to get this blood type, and that is to have one of each of the dominant genes lying together in an example of codominance. So people, what do we see at the end of this? We see that there are 4 possible phenotypes. But when we look at the genotypes, okay, collectively, there are 6 genotypes that code for 4 phenotypes. Okay, and this is the thing to keep in mind over here, that sometimes when it comes to looking at complete dominance, blood group A and blood group B can be expressed genotypically in one of 2 ways, as a homozygous condition or as a heterozygous condition. Okay. The second session of this, or the second part of this session that we need to look at is paternity testing. Okay, and paternity testing often heavily relies on all the work that we have looked at now, and looking at the genes and the combinations, okay, that parents have, and it's used to determine quite quickly whether a person is or is not a father or a mother to a child. And that's quite an important thing. From the beginning, what we need to know is that paternity testing is only used to tell us who is not the father of a baby. Paternity testing on its own is not conclusive in proving who is the father. Okay, so paternity testing, if you only use the blood types of A, B, AB, and O, you are only going to be able to rule out, okay, people who have now either claimed to be the father of the child, or if a mother is claiming things like maintenance and she insists that one man is the father of the child. By doing a blood test, we are only able to tell who is not the father of the baby. Okay, and why is this? Because these are the 4 possible phenotypes, and you know that there are 6 possible genotypes, okay, which code for 4 phenotypes. If we keep it relevant and we just kind of stick to the country and we don't even go globally and outside of our borders, we are sitting at a couple of million people, so plus minus 50 million people are in the country. Okay, if we halve it and we say 25 of those are male, okay, or 25 million rather are male, it is impossible to say that because a father has blood type A and he has a child which has, you know, a certain blood type, that he automatically is that father, because there could be any number of men in the country who have fathered that child. So what you would have to then do to have a conclusive result is you would have to do a DNA test, okay, which is much more conclusive in proving paternity and even maternity Okay, this, for example, can be used if children have been swapped in hospitals or if they've been kidnapped or things like that. Then you might not have any DNA, immediately to kind of use. You might not have a mom that just says, yeah, no, that's my child. If a child's been kidnapped, then you're going to possibly have to choose, or have to prove rather, paternity and maternity. So when choosing or when looking at paternity, it is not enough to only use blood typing. You are going to have to use something else, okay, to prove who is the father of a child. You're going to have to rely on a DNA test. So the only thing we can say in terms of blood typing and linking it to this issue of paternity testing, when using blood typing, is only going to disprove or rule out possible fathers. Okay, it is not going to be enough to prove paternity of a baby. So what I'd like to do now is just run through an example with you. Okay, if we have a look, here are our questions, and it says represent a genetic cross to show how it is possible for parents, both of whom have blood type A, to have a biological child who has blood type O. Okay, so from the outset, what we have to remember immediately, the only way to get a child with blood group O is if you have two recessive genes coming together. Okay, blood type A can be expressed in one of two ways. So let's start very quickly and look at both scenarios. We've said that the parents have blood group A, okay, and they have had a child that has blood group O. Now, if we have parents, okay, let's say that that is the dad, or let's say that's the mom, and let's say that is the dad. If we have that as the genetic composition, as the genotype of the parents coding for that phenotype, if we do it very, very quickly, you're going to see that it will be impossible for these people to have a child with blood group A. Because what you would have is this in your Punnett square. Those two would code for a homozygous dominant condition. Those two would code for another homozygous dominant combination. So would those, and so would that combination. So if you do this in a hurry and you don't keep in mind that we can write this phenotype in a different way, you're going to do this and then you're going to probably think, oh, but there's a problem with this question because these people can't have a biological child with that blood type. But here's the thing, remember, that phenotype can also be written in the heterozygous condition. So both parents are going to have to be heterozygous for the combination, okay, for them to produce a child with that combination.